So we now know how to estimate GLMs using likelihood methods. Now I want to turn to inference for GLMs. First, a word on the parameters themselves. Interpretation of the regression parameters in a GLM is link function specific, and there are two important issues here. First is nonlinearity. Link functions can introduce nonlinear relationships between covariates and outcomes. And the second issue is complexity. For general nonlinear models, the parameters often define particular functions of the response covariate curve, or they render response covariate relationships dependent on other covariates. Now, for these reasons, we can no longer adopt the linear model interpretation of beta j, that is, as the change in y for a unit change in xj. We'll demonstrate parameter interpretation for particular link functions in the R examples at the end of the lecture. First though, let's review the main methods of inference for GLMs. So inference. Distributional results for GLM parameters are not exact. Instead, we make use of the asymptotic results for maximum likelihood estimates that we established in the previous section. So it can be shown that in the large sample limit, beta hat is normally distributed around the true beta, with covariance given by the inverse Fisher information, which for a GLM takes the form X transpose W inverse X transpose W X inverse, with W in the diagonal weight matrix we met in the Fisher scoring algorithm. So it takes that form there. Since W is unknown, the asymptotic covariance matrix is estimated by evaluating W at beta hat, which comes out of the iterative fitting process that we talked about in the previous part of the lecture. Note that because the elements of W involve the variance of yi, the expression can be written explicitly in terms of the scale parameter phi. And if the scale parameter is unknown, it must be estimated. Standard errors for the beta j's are then calculated as the square root of the diagonal elements of the estimated inverse information, and once we have standard errors, then we can get on and do inference. So let's look at some tests that are used in the GLM setting. The first test we want to look at is the wall test, very similar in spirit to the t-test for the linear model. For a null hypothesis that beta j equals some particular value, we construct the test statistic z, the estimate as the estimate minus the hypothesized value divided by the standard error. We call it a z value rather than a t value because it isn't t distributed. It's asymptotically standard normal under the null and is compared to the approximate value from the standard normal table. Typically, we test the null that beta j equals 0 against the two-sided alternative. We can calculate the 100 times 1 minus alpha % confidence interval as usual by inverting this test statistic, the estimate plus or minus the standard error times z alpha over 2. And the walled approach extends to testing a set of restrictions on multiple parameters, for example that all betas are 0, using the walled chi-squared statistic shown at the bottom, which is chi-squared distributed with k degrees of freedom. So that's the wall test. Second test I want to introduce is the likelihood ratio test, which you'll remember from early weeks of the course. It's a very general test of a null hypothesis against an alternative when the null is a constrained version of the alternative. For GLMs, the likelihood ratio test plays a similar role to the F test in the linear model setting. So in the single parameter setting, testing beta equals beta naught, we take the ratio of the two values, the value of the likelihood function at the restricted estimate and the maximum value of the likelihood over all beta values. That ratio, lambda, must be less than or equal to 1 since the restricted fit cannot beat the unrestricted one. The likelihood ratio test statistic is minus 2 log lambda, equivalently minus 2 times the difference in log likelihoods. Under the null, this quantity is asymptotically chi-squared distributed with 1 degree of freedom, and the p-value is the chi-squared probability above the observed statistic. The test extends directly to multiple parameters and can be used to compare nested models. A specific form of likelihood ratio test for GLMs is known as the deviance, and it provides a way of measuring goodness of fit, and it's a standard part of the output of statistical packages, as we'll see later. It's based on the ratio of two values, the maximum likelihood for the fitted model and the maximum likelihood for what's called the saturated model. The saturated model is one that has a separate parameter for each observation, and as such, it attains the maximum achievable log likelihood. It attains a perfect fit, which for an exponential family GLM is computed simply by setting mu hat equal to y. Forming the likelihood ratio test statistic from this ratio gives d over phi, where d is the deviance statistic. Since the fitted model's log likelihood cannot exceed the saturated model's, d is always non-negative. The scale deviance, d over phi, has an approximate chi-squared distribution with n minus k degrees of freedom. The greater the deviance, the poorer the fit. So deviance therefore can be interpreted in a similar way to the residual sum of squares in the linear model context. And in fact, for a normally distributed response, the deviance is exactly the residual sum of squares. Next up, I want to talk about some ways of looking at model fit. The value of the maximum likelihood function is not particularly useful in and of itself because the likelihood will always increase as more parameters are added to a model. Furthermore, likelihood ratio tests are only valid for nested models. So for a general comparison of models, to decide which model is best in a sense, we can use what's called the information criteria, which do two things simultaneously. They reward fidelity to the data, so they reward model fit, but they penalize model complexity. That is, they penalize when models have a greater number of parameters. And two commonly used metrics are ACAI's information criteria and the Bayesian information criteria, or the AIC and the BIC. The AIC is defined as minus 2 times the maximized log likelihood plus 2k. The BIC is minus 2 times the maximized log likelihood plus k log n. For model selection, one approach is simply choose the model with the minimum AIC or BIC. So that would give us the model that fits the data best but is most parsimonious. In general, the BIC penalizes complexity more severely than the AIC, and thus it gravitates less quickly towards more complex models as sample size increases. Okay, the final inference topic I want to talk about is residuals in a GLM, which is much more complex for GLMs than it is for linear models, and in fact there are several kinds of residuals that we can define. So recall that when we defined the random component of a GLM, we didn't do so in terms of an error term. And indeed, the concepts of residuals, as I said, is much more complex. The key issue in the GLM setting is the functional dependence between the mean and the variance. And this creates difficulties in finding a general representation of residuals that have zero mean, constant variance, and a symmetric distribution. So we're going to talk about three types of residuals that are important in the GLM setting. First is what's called the response residual. This is the obvious one. We take the response minus its fitted value, yi, so that is yi minus mu hat I. This might seem attractive as the definition of a residual, predicted value minus the fitted value, observed value minus fitted value, but in contrast to the linear model, the residuals and the fitted values are not in general orthogonal for GLMs, and this residual will have different variance for many types of GLMs, so that means that standardization is required. Looking at these things itself can be quite tricky. This leads to the second type of residual, one that is standardized. It's called the Pearson residual. For a model with variance function v of mu I, the Pearson residual divides the response residual by a quantity proportional to its estimated standard deviation in the fitted models. And Pearson residuals have approximately zero mean and variance phi if the model is correct. And the third type of residual I want to talk about is called the deviance residual. In general, Pearson residuals are skewed And consequently, a preferred form is called the deviance residual. The sign of the response residual, positive where we're underpredicted, negative when we're overpredicted, times the square root of d of I, where di is the contribution of datum I to the deviance. So this is the Pearson residual defined here. Since the deviance is a sum of these contributions, the sum of squares of a deviance residual gives the deviance itself. And this is analogous to the relationship between the linear model residuals and the residual sum of squares. The deviance residuals, or their standardized version, have an asymptotically standard normal distribution. So an examination of residuals can help assess the fit of a GLM and detect unusual observations. For example, residuals can be plotted against the fitted values and against each explanatory variable to detect outliers and assess leverage. Exactly the same logic as the diagnostics we developed for the linear model in lecture 6, and we're going to look at it later when we run regression for GLMs in R.